Welcome to this explainer. We're jumping right into the foundational blueprint of a true computer science legend, Dijkstra's path-finding algorithm. And, we're going to do this by unpacking a highly specific, deceptively simple C code snippet. If you've ever stopped to wonder how your GPS magically gets you from point A to point B, or how internet routers instantly calculate the fastest possible route to blast a message across the globe, well, it all starts right here. So how exactly do computers find the shortest path? It's a massive, massive problem to solve. To really grasp how complex systems navigate these sprawling, chaotic networks, we first need to look at how they set the stage. We aren't even looking at the complex math just yet. We're strictly looking at the architecture. Take a look at this raw C code snippet featuring include standard I/O, our macros, the Dijkstra signature, and the main entry. This 6-line block of C code might look a bit intimidating at a glance, but it's really just an elegant, carefully prepared architect's blueprint for the Dijkstra algorithm. It's the skeleton. Everything that follows, all those miraculous calculations, relies entirely on how these specific lines are structured and defined.
Moving on to the code foundation, let's start right at the top and work our way down line by line to see exactly how we build this architecture from the ground up.
Our very first line is include standard io.h. Think of this as our foundational rulebook. It tells the compiler to pull in the standard input and output library. Without this, our program is basically completely isolated in a dark room. This one simple instruction grants the program the actual ability to communicate with the outside world, to take in our network data, and eventually to print out the fastest route for us to actually see.
Next up, defining the constants. Before any of the pathfinding actually begins, the code has to set the absolute limits of our universe so it can allocate resources properly. We've got two macros here, and we're comparing define max 10, which is our strict limit on grid size, with define INF 999, representing an unreachable infinite distance. We're establishing a maximum board size of 10 nodes and using 999 as a placeholder for that unreachable distance. Let's break those down individually, because they totally dictate how this algorithm thinks about space.
Setting the max to 10 is absolutely crucial. By doing this, the architect ensures the computer knows exactly how much memory to reserve for our pathfinding grid right out of the gate. We're essentially telling the system, hey, do not expect more than 10 cities on this map. It keeps the program incredibly lightweight, lightning fast, and highly efficient. And then we have 999. So, the key takeaway here is this. By setting INF, or infinity, to 999, we're giving the algorithm a baseline starting assumption. It literally assumes that every single destination on our map is impossibly far away, just an infinite distance until it is proven otherwise by finding a shorter, valid path. It's a wildly pessimistic start, right? But that guarantees the algorithm is always hunting for an improvement. Anatomy of the algorithm. Next, we need to define the abilities of our main player, the actual Dijkstra function itself. The function signature takes 3 specific, non-negotiable inputs. Step 1 is integer n, which is the total number of nodes or locations in our specific run. Step 2 is integer cost max, which serves as the map of the network showing the effort it takes to travel between locations. And step 3 is integer src, standing for source, which tells the program exactly where we're standing right now. That cost max parameter? It's simply our 2D adjacency matrix. Think of it as a digital map, where the intersections represent the travel costs between any 2 nodes on our network. For instance, row 1, column 2, simply holds the travel cost from node 1 to node 2. It's just a beautifully simple translation of physical distances into raw digital data.
Tracking the data. Once this algorithm wakes up, it desperately needs internal tools to track its ongoing progress across that grid.
You can think of these local variables in Dijkstra as the algorithm's personal inventory list. Inside the function, we declare a dist array to actively track how far it's traveled from the starting point to any given node, and a visited array to track check nodes. That visited array is basically used to drop digital breadcrumbs. It flags a node as visited so the program doesn't waste precious processing time checking the exact same intersection twice. Actually, if it did that, it would essentially trap itself in a catastrophic endless loop.
The main entry point. Every single C program needs a place to start executing, and this right here is the ultimate command center. Inside the main function, the actual working variables are born. We declare our integer n for our nodes, our source for our starting location, and our 2D grid cost max. Right here, they just sit waiting to be populated with real-world data. Maybe that's the busy streets of your local city, or maybe it's the servers in a vast global internet network. They are primed and ready to be passed directly into the pathfinding engine we just built. So what happens when this blueprint is actually executed? Now that we've established the rules, drawn the board, and placed all of our digital pieces, it leaves us pondering the incredible potential of this simple foundation. What actually happens when we finally populate those variables and turn this pathfinding powerhouse on? Will it map the absolute fastest route across a sprawling metropolitan city? Or is it going to route data packets across the globe in a fraction of a millisecond? That is the real magic of Dijkstra's logic. But I'll leave you to wonder just how that engine roars to life.